One thing that educators think about when developing content for courses is Bloom's taxonomy. You may have seen this before, but let's review it real quickly on how this would work for digital logic. I really love teaching digital logic, and part of the reason is we go the full spectrum of Bloom's taxonomy. We go from the base all the way up to the tip top of the pyramid. So you may have seen this before, and it shows up in various forms, but the idea is that you first of all start with a certain knowledge base. So early on in the course, we're going to be looking at gates and truth tables and Boolean identities and numbering systems. All those things form a base, and then you move up to the next level where you have to show that you understand the knowledge and how it links together to make things happen. For example, you can build a multiplexer out of gates. You need to know what the gates do, but you also need to know what the multiplexer does. Next up is application. We're going to learn some tools. We're going to learn how to describe problems. We're going to learn about truth tables. And then you can apply some of the techniques that we learn from logic and simplification and implementation to make circuits that accomplish different applications. From there, we're also moving up the pyramid where we can do analysis. We can take a look at, for example, a particular digital circuit. We can decompose that based on what we know about our knowledge base and applications and how we understand how things fit together. And we can decompose that system and figure out what it does. All right. So that's another skill level that's on up the pyramid. Next, we develop our skills in evaluating how different designs would work. We could take a look at gate count, for example, and the trade-off between speed and cost. And those kind of things are things that engineers and computer scientists need to use their judgment on to see how things fit together for solving the problem at hand. And then the other thing that I really like about the course is we don't just learn about the theory. It's really pretty easy to go all the way from ground zero, where we're talking about gates. We could even zoom down to the transistor level and understand how those fit together. But more importantly, we can go all the way up this pyramid and actually build circuits that solve different problems. And that's the thing that I think is just really gratifying about digital logic. It's a rare course that lets you go all the way to the top of Bloom's pyramid. So most of the courses you take in engineering or mathematics or sciences tend to stop at the analyze stage. This is a course where you get to go all the way to the top. The next thing I want to talk about quickly is this idea of abstraction levels, because we're going to talk about this often. But one of the things that we do is we have in mind at the beginning what we want a circuit to do. All right, so we're coming up with a design. So we can specify its behavior, and one great way of specifying behavior is through software. So what we're going to learn in this course is that you can design hardware by writing software, but the catch is that you need to have the hardware in mind while you write the software. Okay, so in this example, we have a simple illustration where this is actually a multiplexer. You'll learn what a multiplexer does in a more formal sense later in the course, but the idea is, let's say we have two signals. We want to either pick A or pick B based on an input signal S. All right. So when S is equal to a 0, we might want to pick A. When S is equal to 1, we'd pick B. This can be described formally in Verilog. All right, so the Verilog statement for that, it looks a little cryptic, but the idea is Y gets assigned based on the value of S. If S is equal to 1, we assign it to B. If S is equal to 0, we assign it to A. So sometimes the software is complicated to look at. We'd rather see it in the form of a schematic. It helps us see how different pieces of a design fit together. So this schematic is the same thing as this software, which actually implements this behavior. All right. And then if you drill even further down the abstraction level, this is the circuit for implementing this behavior. All right, so it's just a simple multiplexer. And then within each of these gates, you could drill down to the transistor level. And so ultimately, we have this small behavior. If A and B are scalar inputs and we only have two of them, it takes 14 transistors to implement that. All right. And so making different changes at certain levels can impact the circuit, even though it might be seemingly a trivial change. So, for example, if I wanted to choose from four signals, a 4-to-1 mux, all right, before I only had two signals, A and B. With a 4-to-1 mux, I'd have A, B, C, and D. I'd have two select lines. The implication there is the circuitry gets a little more complicated, and it would take 42 transistors to implement that design. All right, so the point of this video is to tell you a little bit about this process of Bloom's taxonomy. I really like this idea of we build the knowledge base up and we go all the way up to the top of the pyramid where we synthesize circuits. All right, I think it's useful as an engineer and computer scientist when you're learning new materials to think about where you land on this pyramid as you're learning the material, because ultimately our goal is to get all the way up to the top where we can synthesize knowledge and be better engineers and computer scientists.